Hello, hello, and welcome to Unit 1, Concept 1 Notes of Chemistry. We are going to start with measurement because chemistry is a quantitative science. So math is a big part of what we will be learning this year. And I know some of you might be afraid of that. And I want to try to get those fears out of your head, because so much of this is just because of measurements, and you can do measurements. You probably do measurements in so many ways in your life now on a day-to-day basis. So you don't need to be afraid of chemistry. You don't need to be afraid of numbers. And so we're starting with measurements because we are going to be making a ton of measurements this year in lab. And when we make measurements, we want the measurements to be accurate, precise, and we just want them to make sense. So that's why we are going to start with this. So, a little overview that hopefully is familiar to you. Science is all about the experimental design process. And what that looks like is first making observations. It's looking at the world and using your senses in order to make objective observations. So these are things that you do not have an opinion on. They are things that you directly see. So you can walk outside and you can look at the ground and say, the ground feels wet. That is something you can observe with your senses and by touching them. Okay, but then we also take those observations that we make and then we make inferences. Inferences are subjective and they're based on our perceptions. So you can make some observations about the ground and then you can make some inferences like it rained or someone spilled their water cup on the way into school. These are things that we can perceive based on our observations, but we don't necessarily know for sure. And this is often how experiments originally become designed. They start with someone making an observation and then maybe inferring something and wanting to know more. So, a quick practice with observation versus inference before we go any further. I want you to look at this photo and I want you to jot down 3 to 4 examples of observations you can make. These need to be objective. Like everyone in the room could agree on the observations that you make because they are based on your senses and they're like fact. We can all see or observe that. And then I also want you to make 3 or 4 inferences, which are going to be more subjective, more opinions about the pictures you see based on your perceptions. So jot those down so we can talk about those later. Now, once you've made observations, that often leads you to start asking questions. And when you ask questions, then you might be making predictions and predicting the answers to those questions. And that's where hypotheses come in. A hypothesis is a testable prediction, typically between a cause and an effect relationship between variables. And once you make that prediction, you will then want to test that prediction. You'll want to test that hypothesis. And that's where we will be designing labs this year in order to test the hypotheses that we write to answer the questions that we have. Now, once you design an experiment with your independent variable and your dependent variable and your constants, your control group, all these things that we'll be reviewing as we do labs in this class. Once you've designed that experiment, then you're going to want to collect data. And data falls into 2 categories. It can be qualitative or it can be considered quantitative. Qualitative data is based on qualities. So you're going to be using descriptors here like it smells sweet or it tastes sour or the color is red. Okay, whereas quantitative data is based on quantities. So numbers and measurements, which is what this whole concept is about making those measurements. So we're going to be zooming in on quantitative data in this concept. But again, we're going to be looking at all of this in every experiment that we design this year. And like I said at the start, chemistry is one of the more quantitative sciences. It's really math-based. And so we're going to do a lot with numbers. But again, my goal is to not scare you away. You can do this. So much of chemistry is truly just problem solving and thinking critically. That is a skill that's going to carry you through the rest of your life. And so this is such a useful course, whether you go on to use specific chemistry content or not. Okay, but being able to think quantitatively and think in numbers and make measurements is a really, really critical life skill. And then once you collect that data, we will then analyze that data. We will put the data in graphical forms so that we have a visual representation of our data. We'll be making, pie charts. We'll be making bar graphs. We'll be making line graphs. We'll be doing all of those things in this course. And then we'll be looking at the evidence that we've gathered, and we'll be making claims and backing them up with reasoning and that evidence. And so that's where the analysis comes in, which again, we'll practice with our first lab. And then from there, you draw conclusions. We refer back to that hypothesis you made. We look back at the data. We see if that data supports the hypothesis or not. And then often it leads us to ask more questions and to make more observations. And then we continue to kind of walk through a semblance of this process over and over again as scientists. But the reason I gave you this context is, again, just because chemistry is going to be very lab-based. We're going to be walking through this a lot. And a critical part of doing lab is working with measurements, working with quantitative data. And so that's what we're really going to be focusing on in this concept together. So before we go any further in class, I want you to sit and just take an object like the pencil in front of you, and I want you to make a list of qualitative data that you can gather from your pencil, and then also quantitative data. And then that's something we will be talking about as well, just to make sure you really get the difference between these, because both are very valuable in experiments to have both of these things. Also in class, we are going to pause and we are going to do some review of experimental design. We're going to review IV and DV and what you put on an x-axis versus a y-axis, because again, I don't want you to be intimidated by labs in this class. And hopefully this is all review, because this is stuff you've been talking about in science every year that you've taken a science course. But for the sake of this video, we're just going to keep pushing through, and now we're going to start talking more about measurement, which is what, again, this concept's all about. So the best measurements are accurate, precise, and they make sense. So we're going to talk about accuracy, precision, and making sense in this concept. So first, what does it mean for a measurement to be accurate? Accuracy is the degree to which the experimental result agrees with the accepted value. Okay, that sounds very fancy. All we mean is how correct the measurement is. Like, I am 5 feet 5 inches tall. I've been this height since high school. But if someone came and measured me and they said I was 5'7", that is not an accurate measurement because it's not correct. I am not 5'7". I must be wearing heels when they take that measurement, or, a pair of shoes that has a higher, inset on it. But that is not an accurate measurement. So we want our measurements to, of course, be correct. And accuracy is a measure of how close to the truth a measurement is. So, of course, we want accurate measurements. But we also want precise measurements. Precision is the degree to which measurements agree with one another. And so you can kind of think of this two ways. First, how specific the measurement is. Okay, so you wouldn't just say, oh, she's about 5 feet tall. That's not very specific. 5 feet 5 inches is a much more precise measurement of my height. So we want specific measurements. We want our measurements to be as specific as possible. And then we also want them to be consistent. Like, you could take the same measurement over and over again and get almost the exact same, if not the same, measurement each time. So if 10 of you in this class measured my height and you all got a range of heights from me, those are not very precise values. Those are not precise measurements because your measurements aren't consistent with one another. So something's going wrong here. We're not using the measurement tool correctly. Okay, so we want our measurements to be precise, meaning specific, but also consistent. Like, we can repeat that measurement over and over and keep getting really, really similar results. When you are making a measurement in a lab, to get the most precise answer, we often will estimate 1 digit past the amount you can read on the instrument. So for example, if you're looking at a graduated cylinder and you're measuring the volume of some water in it, you'll be able to read the little dashes that are on there, but then you're going to estimate 1 digit further. So if you can read that it's like 17 milliliters, but it's kind of between the 17 and 18, then you're going to estimate 17.5. Or if it's a little bit closer to the 18, maybe 17.8 or 17.9 milliliters for your measurement. So we're always going to take it one step further. Another thing with precision is how repeatable your measurements are. Again, with the consistency, are we getting these same types of things over and over again? That's what we're really looking for here. And like I said, chemistry is a quantitative science. This course is filled with numbers, and so we want them to be both accurate and precise, the numbers that we're working with. Consider a sniper. A sniper has to be both accurate, they need to be correct in their target of what they're trying to shoot, and they need to be precise. They need to be able to make the same shot over and over again so that they can be trusted to do their job. Okay, so let's look at these images as a visual representation of what we can see with accuracy and precision. So consider a bullseye. The center is the target. So that would be the correct place to hit. And notice this person who is throwing darts. They threw 4 times and they're all right there in the center. We would say that this dart thrower is both precise and accurate. They're consistently hitting the same spot and they're also hitting the correct target every time. Now in this next picture, this person is pretty consistent, but they're not accurate. They're doing the same mistake over and over, and it's getting them to just miss the target. So we would say that this is a visual of someone being precise, but not very accurate. Okay, next right here, this person is seemingly pretty accurate. They're almost all right there where the target is, but they're not like hitting the same area very much. They're not very precise. So they're accurate, but not precise. And then this person really doesn't know how to throw darts. They are not accurate. They are not precise. They're neither. So that hopefully this is a visual that helps you understand the distinction between those two terms. But again, we just really want when we're making measurements to be both. We want them to be precise and we want them to be accurate. Okay, but we're not perfect. You will make errors when you make measurements. It's just part of it. And that's where being able to calculate something called your percentage error is very important. So your percentage error shows how far off a measurement made in lab is from the commonly accepted value. So like we said earlier, I'm 5'5". That's my commonly accepted value for my height. I'm not growing anymore and I hope I'm not shrinking. And if you measured my height to be 5'7", we would calculate the percentage error in your measurement. Like how far off were you? And here's how we do that. You take your experimental value, so the measurement you made in lab, and you subtract the accepted value from it, and then you divide by that accepted value. Now, you could get a negative number, okay? You can get a negative number, but that's where these are absolute value signs. So basically that just says we're going to take away the negative. So we're not going to worry about whether it's negative or not. We're just going to make it positive. And then we're going to times by 100 to get a percentage here. So this is how you're going to calculate the percent error. Okay, so here's an example. Let's say you calculate the density of a substance in lab to be 2.10 grams per milliliter. Now, the substance's correct density, like the answer in the answer key you should have gotten, is 2.17 grams per milliliter. What would be your percentage error, your percent error in this? Okay, so first, what do we know here? We know the experimental value, what you measured or what you calculated was 2.10 grams per milliliter. And we know that the accepted value, what the correct number that's like commonly accepted is 2.17 grams per milliliter. So if we're looking for percent error, this is what our background information is, okay? I like to draw a line to separate what I know from what I'm trying to find out. Keeps me organized. Okay, so let's plug in this equation here. Percentage error equals your experimental value, which is 2.1, minus your accepted divided by your accepted. We're going to take the absolute value of that and then times by 100. Okay, so when we do this, we get 3.23%. And that is the percentage error that we were off in our measurement. So this is a skill that we're going to be practicing over and over again in lab, and I just want to introduce it to you here. Now, another thing we can do to try to mitigate errors that are going to happen is to increase our sample size or the number of trials that we are doing in a lab. So we don't just want to make, a measurement once and then that's it. We want to make that measurement several times to make sure that we're being precise and that we are getting consistent measurements over and over again. And then oftentimes when we do this, let's say we do 10 different trials, then we're going to need to calculate an average. So instead of looking at 10 different values for the same thing, we can just look at one value that represents all of the values, and that would be your average. So an average is just a sum of the values divided by the number of values. So here's an example. Callie measures her flower to be 31 centimeters tall. Jay measures the plant to be 45 centimeters tall. Liam measures the plant to be 35 centimeters tall. Find the average of their measurements of the plant's height. So first, we're just going to find the sum of those values, 31 plus 45 plus 35, and then we'll divide by the number of values, which there are 3 measurements, so there are 3 values, so we will divide by 3. So we add those up first. We get 111 centimeters divided by 3. When you input that into your calculator, you get 37 centimeters. And that is an example of how you will calculate an average. Now let's talk about standard units. There are a variety of units we can use to represent our measurements, but standard units are really, really helpful. So a standard is just an exact quantity that people are going to use for comparison. And the SI system specifically is a system used by scientists around the world internationally to make measurements. So basically, we sat down and we had a bunch of scientists decide these are the measurements that we're going to use, so that if we're sharing data with each other, it's a lot easier to do that because our measurements are written in the same units. Now, each type of measurement has a base unit, and then we use prefixes to change the base unit based on multiples of 10. And the reason we do this, which we'll talk about a little bit more, is because, again, we want our measurements to be precise and accurate, but we also want them to make sense. And in order for them to make sense, we don't want to have giant numbers or really tiny numbers to look at. That can get a little confusing. And so that's where we're going to use prefixes and we're going to use different units in order to make our numbers just a little bit more manageable to work with. Okay, but let's talk about those standard SI units. So length is a measurement we will be making in lab a lot. It's the distance between 2 points. You're going to use a ruler or a meter stick or something to do it. And the standard SI unit for length is the meter, which is abbreviated with an M. So that's a unit that you're going to need to know and we'll be using a lot. Okay, mass. This is the amount of matter in an object. The unit that's the SI unit for mass is the kilogram, which is abbreviated kg. And we're going to use digital scales. You can also use a spring scale like this one pictured. Those are different ways that we can measure the mass of an object. Okay, another standard unit to know is time. Time is just the interval between two events, and our standard SI unit for that is seconds, which is abbreviated as just an S. And we'll use a stopwatch to do that regularly. Oftentimes you may be using your phone too. Now, one that might be new to you, and I want to introduce to you early and often because it's going to be your friend, is the amount of substance. And that is measured in moles, which is abbreviated MOL. They just cut off one letter for us. So it's not this kind of mole, but it's a different kind of mole. It's used for measuring large amounts of really tiny things. So chemistry is all about atoms, which we'll be talking about. And atoms are really, really tiny. And so there are lots of atoms in lots of things. And so in order to talk about them in a way that makes more sense, we're going to use moles to do that. So what's a mole? If you have 1 mole of something, you have this much of it. Okay, that's an insane number. In scientific notation, which we'll be talking about in concept 2, and reviewing that, hopefully it's a review for you. That's 6.02 times 10 to the 23. That's how many place values we had to move to get to this number. Okay, that's 1 mole of something. So this picture is cute of this mole. I love it, but this is not the kind of mole we're talking about. We're talking about this kind of mole. And again, don't let this overwhelm you. I'm just introducing you to the mole now. It is going to become your friend all year long. Don't worry. Another standard unit we need to talk about is temperature. And I put a star here because the definition I put in here is that temperature is the amount of heat in an object. And while that is somewhat true, there's a lot more to temperature. We're going to talk about kinetic energy and some other things later. So we're going to save that for a later unit. But for now, temperature, just think of it as the amount of heat in an object. And the SI unit for temperature is Kelvin, which is abbreviated as a capital K. Now, this is different from the metric system, which uses Celsius. And this is also different from the United States, which were the only ones really hanging on to Fahrenheit. So these are very common units for measurement of temperature, but we're going to be using Kelvin in this class. And so you need to be able to convert between these measurements frequently. Okay, and so we'll practice that. We'll take measurements using thermometers, but then we're also going to convert those measurements. And like I said, we'll learn a more scientifically accurate definition of this in the future, which we will write down. So don't worry about that. So temperature conversions. To get Kelvin, if you know the amount of the temperature in Celsius, you can always get Kelvin. All you have to do is add 273.15 and you get Kelvin. And you might be thinking, this is so random. This is so big and obscure. Like, where did this come from? The purpose of Kelvin is so that we don't get negative numbers. And it's because, again, temperature is really looking at an amount of heat. So how can you have negative heat? And so that's where Kelvin is the accepted SI unit for this. But again, it's okay. We're going to just use conversions, and that's where you'll always be able to get it where you need to if that is the case. Now, if you have Fahrenheit and you want it to be in Celsius so that then you can get it to Kelvin, you're going to use this equation. So we always do the parentheses first. So you're going to subtract 32 and then times it by 5 and divide it by 9. And then also if you have Fahrenheit, you can or Celsius, you can convert to Fahrenheit this way as well. So times by 9, divide by 5, but then add 32 at the end. So we're going to practice using these as well. Quick side note before we do an example. There are other SI units too. There's the ampere, which is for electric current, and there's the candela, which is for luminous intensity. But I don't want you to worry about those because those aren't things we're really going to be measuring in this class. I just want you to know like Kelvin for temperature, seconds for time, kilograms for mass, that kind of thing. Now, you may already be like, what are you talking about? What is this foreign language right here? I'm not into this. Okay, so I don't want you to be overwhelmed. You can solve any problem as a chemist, and I'm going to help you do that with a strategy called radar. Like I said in the beginning, chemistry is all about problem solving, and you can solve any problem with the radar method. So if you are given any sort of problem and you don't know how to follow it, don't be defeated. Just do radar. So what does radar stand for? The R stands for read. I want you to read the problem and ask yourself, what am I looking for? What is this question asking me? Then you're going to analyze. What information did we get? We're going to write our knowns and our unknowns. Okay, what numbers do we know? Let's label those. What numbers are we trying to figure out? What do we not know? Let's label those. Then you're going to diagnose. What can you do with this information you have? Let's make a plan. Let's find an equation that works with the values that we know and don't know and are trying to figure out. From there, you'll assess, you'll carry out that plan or you'll solve that equation. And then you're going to reflect. This is so important. You're going to look back and say, is this answer reasonable? Like if you're measuring the temperature of something and you get the temperature to be 10,000 degrees Fahrenheit, does that seem reasonable? That seems like a crazy number. Okay, so we really want our measurements, again, to make sense. And that's where the reflection portion is really, really important. Sometimes you're just doing something as simple as a calculation error in your calculator. And it's not like you did the whole problem wrong. You just punched in the calculator wrong. So you ended up with this crazy number. And that's where we always want to reflect. That's one of the really simple ways you can often catch the mistakes that you're making. Okay, so let's talk through another example. Mrs. Benton is pregnant. Her body is super sore and she would like to take a bath. Her doctor told her this was fine as long as the bath wasn't more than 98 degrees Fahrenheit. She finds a thermometer in the junk drawer and places it in her bath water. It reads 38.5 degrees Celsius. Is she safe to take a bath in this water? Okay, so we just did R. We just read. We read the problem. Now we need to analyze. What do we know? What values do we know? We know that her bath water is 38.5 degrees Celsius. We need to know and we want to know what her bath water is in Fahrenheit so that we can know if she can take a bath or not, because she can't take it if it's above 98. Okay, so that's what we're trying to figure out. Is it that or not? So we need to figure out the Fahrenheit. Okay, so now let's diagnose. Go back and let's look at some of these equations that we've had. Which one of these makes the most sense? We know Celsius and we're trying to find Fahrenheit. We want what we're trying to find to be by itself. And so that's where this last equation is going to be the most helpful for us. Okay, so again, what we know, what we don't know, this is the equation that's going to be the most useful for us. Now, again, I like to then draw a line. So I like to keep my analysis and my diagnosis on one side and then all of my assessing and reflecting on the other side so that I can stay really organized. Okay, so let's write out the equation. So let's write it again, but let's plug in for degrees Celsius. We know it's 38.5, so we're going to plug that in here. Okay, now let's solve this. We always do parentheses first in terms of order of operations. So 38.5 times 9 and then divided by 5 is 69.3. Now we're going to add 32, and that gives us 101.3 degrees Fahrenheit. So is she safe in the bathwater? No, she is not safe. This is too hot. The doctor said only 98, and she's at 101.3. She's going to have to let that bathwater cool down if she wants to safely take a bath. Okay, so you can do this strategy with any problem, and we're going to practice it all year long. Don't worry. Okay, again, so like we said, we want measurements to be accurate, we want them to be precise, and we want them to make sense. That's the other thing that we want. And so one of the things that we're going to do, like I said, is we want to make sure that measurements aren't giant numbers or tiny numbers. We want to write them in units that make the most sense. So for example, if I wanted to know how long you could hold your breath, you can probably only hold it for a couple minutes. So it wouldn't make sense for you to tell me how many days you can hold your breath for, because you probably can't even hold your breath for a full day. You would not live. So we want our units to make sense. Okay, so let's talk about this. How many seconds are in 1 minute? Just off the top of your head, you know this answer. There are 60 seconds in 1 minute. That means that 60 seconds equals 1 minute. 1 minute equals 60 seconds. They're the same exact thing. If I told you something takes me 60 seconds to do it, that's the same thing as me telling you it takes me 1 minute to do it. Okay? Another question. How many minutes are in 1 hour? Well, there's 60 minutes in 1 hour. So let's say I wanted to tell you how long it takes me to drive home. So if the answer is 15 minutes, but I wanted you to tell me in seconds, how many seconds does it take me to get home? I can figure that out. Because there are 60 seconds in 1 minute, I can determine that 15 minutes is equal to 900 seconds. I just have to multiply this by 60, and then I know how many seconds it is. And because I know that there are 60 minutes in 1 hour, 15 minutes is equal to 0.25 hours. So these are some calculations that we can do. So I can tell you, I can say it took me 900 seconds to drive home, or I could tell you it took me 0.25 hours to drive home. But it makes the most sense if I just tell you it takes me 15 minutes to go home. Okay, so why am I saying all of this? I'm saying all of this because this is an example of why we use something called conversion factors. They help us make sure we're making measurements that make the most sense. We're going to use units, like in this example, minutes. That makes way more sense to measure this than hours or seconds. Okay, so conversion factors. These are just ratios of equivalent values, meaning they equal 1. When you need a measurement in different units without changing the value of the measurement, you don't want to change the value of it because then your measurement isn't accurate anymore. But you want to convert the units it's in, so you're going to use a conversion factor. And this is so useful and so practical. Y'all are probably doing this in a lot of ways in your life and you don't even realize it. Okay, so for example, baking and cooking. Like if a recipe calls for something in grams, but you don't have grams as a measurement tool, you only have your teaspoons and tablespoons. You may need to do some conversions there. Or let's say you have a recipe for how to make 10 pancakes, but you need to up that recipe to make 25 pancakes. You have more people coming. So you got to figure out how to convert all of the measurements in the recipe so that you can make more pancakes. This is something that happens all the time in baking and cooking. You're constantly going to do it in your head. Another way this is useful is with traveling to different countries where they're going to use different currencies and being able to calculate before you buy a souvenir. Is this something I can afford in this unit? You got to know how to convert that. Another thing is purchasing products from different countries. A great example of this is the formula shortage that happened in the United States in 2022. So US formula for babies, infant formula, is measured often in ounces. So a parent will know that, okay, I'm going to have 8 fluid ounces of water and then I add 4 scoops of formula. But a lot of parents were forced to use European formula brands because of the US formula shortage. And when those European formulas came over, their measurements were done in milliliters. And so we have bottles in the US that only have ounce measurements on them and ounce lines on it, but you got to know how to convert that to milliliters in order to figure out how much to feed your baby. So I know this sounds like, when you hear conversion factors and you hear what I'm talking about, you're like, am I going to use this? You will be shocked how much you actually need to know this. This is also really big for building. My brother is a civil engineer. And when they process design, it's all done in metric. But then the people in mechanical design who are doing like HVAC and piping and stuff like that, they're using the imperial system. And so they're constantly having to convert each other's measurements to make their plans work together and make sense. Okay, so this is really big in building and engineering. Okay, so let's talk through an example. There are 24 hours in one day. So therefore, these 3 dots mean therefore. It's an abbreviation I like to use in making notes so I don't have to write as much. So know that that's there and you're going to see that a lot. But this means therefore. There are 24 hours in one day. So 24 hours equals 1 day. This is a conversion factor. 24 hours equals 1 day equals 24 hours. That's a conversion factor. Okay, so we're going to use those to convert measurements into different units that make sense. This often also requires us to use prefixes. So again, I mentioned this earlier, but prefixes are used in measurements to avoid really large or very small numbers, and they attach the unit name. So a milligram, milli is a prefix, and that gives us milligram, mg, as opposed to just gram or g. So if I'm measuring something really small, I'd probably rather use milligram than gram. Okay, so there are a bunch of these. One of the prefixes is mega. 1 mega of something is, 1 million of it. 1 kilo of something is 1,000 of it. And I say base unit, that's going to be like meters for length, grams for mass, liters for volume, seconds. So you can have, centigrams, milligrams, hectoliters, kiloliters. These are things we can add on here. And it all just, again, depends on what you are measuring. Okay, so what this means, again, what the heck does this mean? 1 kilogram, that's what this means, is the same as 1,000 grams. We're just putting in a base unit for grams. 100 centimeters is the same thing as 1 base unit, 1 meter. I can use these values as conversion factors so that my measurements are written in units that make the most sense. Okay, now there's a foolproof process you can use every time you need to make a conversion like this. So first, you're going to write down the given number and unit. Then you're going to draw a picket fence, something like this. And then you're going to use a chart to fill in appropriate conversion factors. These are going to be given to you. I'm not expecting you to memorize these. And the most important thing here is you want the units to be on opposite sides of the fence so that they'll cancel out. This will make sense in a second. Then you multiply across the top and across the bottom, and then divide top and bottom, and that will get you your answer. Okay, this is one of those things, I promise, it's much easier when you're actually doing it. So let's just do an example. Okay, let's say I want to know how many meters are there in 51 kilometers. Okay, so think through radar, think through the steps we've talked through. What do we know? We know kilometers is 51. What do we want to know? We want to know meters. Okay, let's diagnose. What can we use that will help us? Okay, look at there is a reference sheet for you that has a bunch of conversion factors for you that you can look at. So let's look at that and see, is there anything that connects meters, which is a base unit, to kilometers? And you may see that, oh, there's 1,000 meters in 1 kilometer. Okay, so now we go through the unit conversion steps. We're ready. So we write down the given number and unit, that's 51 kilometers, and then we draw a picket fence. Now we're going to put in a conversion factor. 1 kilometer is the same as 1,000 meters, but we're going to put the units in opposite ends. We want 1 kilometer down here, and we want 1,000 meters up here. You could put it either way, but we want it this way so that these will cancel out. Those kilometers cancel out, and that leaves me with just meters left. Then we multiply across the top. What's 51 times 1,000 meters? Well, it's 51,000 meters. You multiply across the bottom. We just got a 1, so it's just 1. And now you divide the top by the bottom. 51,000 meters divided by 1 is just 51,000 meters. So how many meters are there in 51 kilometers? There's 51,000 meters. Okay, let's try another one. How many kilograms are there in 12,135 milligrams? Well, what do we know? We know how many milligrams, and we want to know how many kilograms. What are some things we can use to diagnose this problem? Well, let's look at our sheet. Look at your reference sheet. There's 1,000 milli in 1 base unit. So there's 1,000 milligrams in 1 gram, which is the base unit for mass. We can also see that there's 1,000 base units in 1 kilo. So 1,000 grams in 1 kilogram. And now we can use these to get there. So first, we write what we know, our given number and unit. That's 12,135 milligrams. We draw our picket fence. Now, I have to cancel out the units, so I got to put milligrams in the bottom. So I'm going to put 1,000 milligrams in the bottom, and that's the same as 1 gram. That's my conversion factor. Okay, so now I've gotten rid of milligrams, but now I got to get rid of grams. So I'm going to use my next conversion factor, 1,000 grams in the bottom and 1 kilogram on top. This allows me to cancel out milligrams and cancel out grams, and I'm left with just kilograms, which is what I was looking for originally. So now I multiply across the top, 12,135 times 1 times 1. And then I multiply across the bottom, 1,000 times 1,000, which is 1 million. And then I'm going to divide here, and I get 0.012135 kilograms in 12,135 milligrams. Those are the same thing. That's a unit conversion. Okay, so now I want you to pause the video, and I want you to practice this on your own and do the work and see if you can figure out these answers. And then in class, after we go over those, we're gonna do some measurement practice. We're gonna be looking at values, determining what unit makes the most sense, and then we're also gonna practice making some measurements as well. But for the sake of the video, because we gotta finish this out, this is a long one, y'all. I'm sorry to get us started long. That's why we're breaking it up in class with some different activities and practice. But for the sake of this video, let's keep going and let's talk about sig figs, okay? So remember, again, I've said this over and over, the best measurements are accurate, they're precise, and they make sense. And so something that we often need to do then is utilize significant figures. So significant figures or significant digits or sig figs are the number of digits in a measurement that reflect how accurate the measurement is. And really, y'all, all you really need to understand for this is you really need to know how to round your answers from your calculations. So if you're doing a calculation and you get a number like 8.3333333333 repeating, how specifically do you need to round that? Like, what are you going to write down? Because you're not going to write 8.3 and just keep writing threes until you run off your paper. So it's going to help us know how to do that. And it also helps us ensure that the numbers that we're getting from our calculations are not more precise or more specific than the measurements that we started with. So if you measure the volume of something to be 18 milliliters and then you measure the mass to be like 100 grams, and then you divide those to find density and you get this number like 4.879247. Like, that's so specific. That's like a number that an astronaut could maybe get from NASA. Okay, we're not NASA astronauts. It needs to be a less specific number because we started with less specific numbers. And that's where sig figs come in. Okay, so for example, density is mass divided by volume. That's what I just mentioned. D equals M divided by V. So find the density of a penny. Okay, so if we're looking for density, that means we need to know mass and we need to know volume in order to do that. So we would take the mass of the penny and find that using a digital scale. Then we would find the volume of the penny. We could do this with water displacement, which I'll show you in class, or you can calculate it if it's a traditional shape, which a penny kind of is. And then we'll divide those. And I'll do an example of this in class that'll show you how important it is to know how much we're going to round for this. There's also a video I'll show you too that'll help. But basically, there are some rules, and I'm going to give you these rules, and these are always going to be available to you. You don't need to memorize these if you're my student, okay? Other teacher students listening to this, they may make you memorize. Mine, you don't need to memorize. I just want you to be able to use them, okay? So how do we know what's significant and what's not significant? What counts and what doesn't count? How do we know how to round? Here's what we know. Here's what's not significant. Placeholder zeros. So zeros that are just there to take up space. What is significant is everything else. Non-zero numbers, 1, 2, 7, 9, 4, those always count. Okay, so for example, 411 has 3 significant figures because it has 3 non-zero numbers, 1, 2, 3. All of those are significant. Okay, another thing that's significant is sandwich zeros. So meaning they're between non-zero numbers. Okay, so look at this example. In 404, this 0 is significant because it's between 2 non-zero numbers. So we would say that this number has 3 sig figs. 1, 2, 3. But in 440, that 0 is not sandwiched. It's just a placeholder. It's just there to let you know that this is 440, not 44. And so this number only has 2 sig figs. Okay, that's important. And then another thing that is significant is trailing zeros when a decimal is present. Okay, so if there's a decimal, the zeros at the end, those matter. Okay, so looking at this 0 doesn't matter. It's not trailing, it's not the end. But these do because they're after the decimal. So this number right here has 3 sig figs. Right here, though, only has 1. Because remember, these are just placeholders. They're just placeholders, which are never significant. Right here is also only 1 sig fig. Okay, because all of these are trailing, but there's no decimal. Okay, so I want you to practice this. I know that could really seem overwhelming. I want you to practice this. Try to determine how many sig figs are in all of these measurements and write those down on your paper. We'll go over these in class and we'll do a lot more practice too. All right, that's your introduction to measurements.